Okay, so what we are doing today is that we are using FVM method to write the equation. Okay, so the problem before us is this is a you have this steady flow heat equation, conduction equation, that is our problem, with a uniform heat generation. Okay, and the faces, the boundaries are maintained at constant temperatures. Left and right boundaries are there. Okay, now the diffusion coefficient gamma, that is K, okay, amount of heat flow per unit area per unit time. The heat conduction problem becomes the thermal conductivity K for the material. Thickness of the plate is 2 centimeter, and it's a thick plate, infinite in two directions, depth wise also, height wise also. So you have only one dimensional where the variation is there. K is given to us. Temperatures of the left surface TA and TB are 100 degree C and 400 degree C. Okay, and heat generation within is 500 kilowatt per meter cube. And now we have to solve this. Let me just show you this on the diagram. This is our plate, which is here, I think it was 2 centimeter thickness. Now this side we have infinite, and also this side we have infinite. Okay, this side TB is equal to 400 degree C, and this side is TA is equal to 100 degree C. Okay, now how we are going to do is, assuming that the dimension in y direction and z direction are so large that the temperature gradients are only significant in x direction. So we are assuming that temperature is varying only in x direction. We reduce the problem to one dimensional analysis. We applied the finite volume method to obtain the solution of this simple heat conduction problem. So what we are going to do, we are going to go up to the formation of matrix, which can be solved, and then we can get the temperatures. And the solution of the matrix we will be doing later on. Okay, so how do we go about doing it? Let us divide the domain into 4 control volumes. Now you can divide in 10 also, 20 also, as you wish, depending upon the accuracy. Here we are doing just to show that how it is being done. Delta x is the width of each element. It is equal to 5 mm. So you have 5 mm into 4 elements, you get 2 centimeter. This is the thickness. Okay, now this is the, and so you will have 5 mm into 4 is equal to 2 centimeters. So this is how you will divide into 4 parts like this. Okay, there will be 4 sections. Now we are blowing up this problem. It's like this. So this is our left edge TA, this is our right, this is equal to 400 degree C. We are using as a constant so that we can change it later on instead of putting the value, and here it is 100 degree C. Okay, now the division is made such that you have these 4 elements, they are of same thickness. Now they are your control volumes. They have a thickness of delta x, and you can say depth of 1 meter or unit depth and unit height. Okay, and these are the centroids, 4 centroids. Okay, and on these 4 centroids we'll be finding the values. What are the steady state? That means after the end, what will be the values here? Okay, this x is equal to 5 millimeter. Okay, now you recall that, or see that, note it, that this is the point P on which we are writing the equation. So the point on the right is called east and the point on the left is called west point. Of course, when you take, because you are writing equation for all the points, as you move next, so this E will become P, this will become your east, and this will become your west, right? And when you are having here, let us say you are talking about this point, okay, when you will be talking about this point P, this will become your east and this will become your west. Similarly here, this will be P, this will be east and this will be west. So only thing is, when I talk about east, that means you are on the right, talking about a point on the right. When we talk about west, we are talking about a point on the left. Otherwise, point number are 1, 2, 3, 4. They are distinct, because east, a point is east at present, then it will become west also. So that creates a confusion. The real point numbers are 1, 2, 3, 4, TA and TB. Okay. Now, what we are doing is, we are applying this equation of conservation inside element 2 and 3. So this is your element 2 and this is your element 3. You are applying equation at these elements. For inside elements, the equation is like this. We have seen this equation. This is the heat flow inside the element 2 or whichever element is from the right side. This is the heat flow in, if you take with the negative sign, from the left side. Okay, and this is the heat generation. So all the heat flowing in plus heat generation, that should be 0. Okay. Now what we do, that this term K is constant, A comes here as is. So delta T by delta X is written as central difference stream. You take a point, where you want to find out derivative at this point. So you take the right point E, left point P, divide by delta X. Earlier we had 2 delta X, but here it is half delta X on both sides. So it is basically twice into delta X by 2. For central difference, the division is by twice delta X, if you recall. But here delta X is here, delta X by 2. You can see here, delta X is this much, this is delta X, and this much is half delta X. This is half delta X by 2. This is also half delta X by 2. Okay. So this becomes your derivative. Similarly, on the west side, you are again taking the central difference, Tp minus Tw. The small, this, remember, this E point is in between E and P, and this W point is a smaller point. This is between P and W. Okay, so you write it. Now you put the values here, and I will not go much into it. It is all mathematics. Finally, what we are doing only is, TPs are collected on the left. You have 2 values for TP. One is here, one is here. So, and you have this TE and TW. So TE and TW are kept on the right side, S phi is kept on the right side, and your TP is written on the left side. Okay, it's a simpler rearrangement. Now this Ka by delta x by delta volume is nothing but K by delta x square, because your delta volume is equal to A into delta x. Okay, so then we are putting the values for it. K comes out to be 2 into 10 raised to power 5 K by delta x square, and S phi is 5 into 10 raised to power 5. That you can calculate from the data. So you get the equation 4 into 10 raised to power 5 Tp is equal to 2 into 10 raised to power Te plus 2 into 10 raised to power 5 Tw plus 5 into 10 raised to power 5. The equation you get is this. Now this equation is written for point P, right? East and west are points to this. As this equation is valid for both nodes and node 3, now we will, because for all the internal nodes it will be same, unless until there are some variations, like there can be variation, lengthwise variation may be there. But if it is the distance between nodes is same, you will not get. So Tp is your point 2, the right point is T3, left point is T1, and this is your 5 coming here. If you write the same equation for point 3, right, so then this actually should be here. This 4 will be on the right and 2 will be on the left, and 5. So you get these two equations for point 2 and 3. Now you have to write equation for 1 and 2. Now applying equation of conservation for left element 1. Now when you are writing equation for left 1, point 1, this is the point on the left. Now you have to remember here that on the left side you have this is equal to delta x. Delta x by 2. On the right side this is equal to delta x. So this element is slightly different. Now when you are finding derivative at this point on the left side, here you will be using forward difference, because there is you want to find derivative at this point, there is no point on the left side. So for point 2 and 3 you are using central difference to find the derivative at their boundaries. Point 2 का जो boundary है वो 2 और 3 के बीच में है और 1 और 2 के बीच में है, और वहाँ पर जब डेरिवेटिव निकालते हैं तो हम सेंट्रल डिफरेंस से निकालते हैं, बिकॉज देयर आर पॉइंट्स ऑन द बोथ साइड्स अवेलेबल टू अस. बट हियर देयर इज, if you want to find out derivative at the edge left boundary, you cannot find it by the central difference, you have to go by forward difference. Similarly, when you are talking about this point TB, you have to find derivative here also. Here we will use backward difference instead of central difference. Okay, so this you remember. Now when you write about W, the equation is like this. Again same equation, delta x, delta t by del x at E and delta t by del x at W. Now when you write this derivative at E is to the right. To the right is your TE minus TP. T is on the right, TP is the current point. this is 1, this is 2. So this is 2 minus 1 divided by delta x. Now when you finding the derivative on the west side, you have to do forward difference method. Okay, so this will be Tp minus Ta. Okay, and that will be you are finding W. W जो है आपका जो पॉइंट है वो 1 है. ओके, तो ये जो डेरिवेटिव आएगा W नहीं Ta है. W इज द पॉइंट Ta, वेस्ट इज Ta. तो Ta पे आ जाता है 1 माइनस Ta बाय डेल एक्स बाई 2, बिकॉज नाउ लेंथ इज हाफ. ठीक है, ये आ जाएगा. And you will fill both these into this equation. Simple substitution. You will get this something like this. This equation. Okay. Rest all is mathematics. Tp you are bringing on the left side, then Te on the right, and Ta on the right. Okay. Tp, Te, Ta. And finally Tp, Ta, Ta, and what will happen? Your Tp is 0.2. Now this is the equation you get. Tp is 0.2. Sorry, Tp is 0.1. Te on the east is 0.2, and Ta you have here. So you get this equation, and a similar equation you will get for 0.4. Okay. Now 0.4 is this, and again you write two derivatives here, right? And on the left side, east side, the derivative will be backward difference, Tb minus Tp by this. On the west side, it will be central difference. Okay, and you combine the two. Okay, these are just conversions, and you get the equation like this. Okay, now we put all the four equations together. These are the four equations you have got, and you can solve them. Whichever method you use, you can find value of T1, T2, T3 and T4. Ta and Tb are known. You can adjust their values also, change their values also, and you will get the. Now, in the book from where I have taken the example, he has actually multiplied all this equation by 500. For some reason, that he has not simplified it to the next level. So you will get these equations. There is no difference between the two. Only thing is, if you refer to the notes, you will get these equations. Okay. Now, when you solve this you get a matrix of this form. Right? Your Ta and Tb are known, so they are brought on the right side. So this column is known to you, right side. These are your unknowns, and these are your coefficients. You can solve this by matrix inversion or whatever it is. But one thing beautiful about this whole thing is where you have to note, and from where we will start the next thing, from the next lecture, that this matrix is a special matrix. Right? It is called tri-diagonal matrix. The three diagonals are these. Of course, you have these diagonals also. So in total you have 3 plus 4, 7 diagonals. Okay, but other than the 3 central diagonals, all others are 0. So such type of matrix in CFD called sparsely populated matrix. Now there is a special way of solving them. Now suppose your problem was 2D, then what will happen? Can I? Okay, I'll have to. Now suppose your problem was 2D, then what will happen? This is your point P. This will be east, west, north and south. So TP will be written in terms of TE, T west, T north and T south. Right? Now that matrix, if you write this, solve in 2 dimensional, that will become 5 diagonal matrix. Okay, and the other one will be 0. If you go for 3D, so this is for 2D, it is this. If you go for 3D, TP will have 6 of them, 6 neighboring points. So there will be 7 axes, 7 diagonals which will be significant, remaining all will be 0. Because this is so far if you are focusing on central difference. Central difference goes only 1 point to the right, 1 point to the left. If you want to still go further, you can have 2 points on the right, 2 points on the left. If you start going like that, then as many points you are considering, as many diagonals will be added. Okay. Now let's come back to this. So you solve this matrix. There are number of ways of solving it. But remember that when you have this points in millions, right? So you will have this as a, suppose you have 1 million points. So you will have matrix of 1 million by 1 million. Right? So for 4 points you have a matrix of 4 by 4. For 1 million points it will be a matrix of 1 million by 1 million. And of course even computers cannot solve it. If you go by the normal method, a foolproof method of Gauss elimination or matrix inversion, you will not be able to solve them in a reasonable amount of time. So again you have to do the approximation. I was saying this matrix will be 1 million by 1 million if there are 1 million nodes. Okay? So you have to resort to. So again you are going by approximation. And you do not know that approximated method will give you. So again you have to, now your exercise is what? You have to see that your approximate method reaches to the final solution in the fastest possible way and it gives you accurate result. Right? So that type of exercise is left. So this is how we go about doing it. This is as far as the FVM was concerned. Same thing can be done for FDM. In FDM, we will also do an example, maybe tomorrow, by Crank-Nicholson method, where you can actually solve the problem. There will be a type of a problem. You write an equation, then you write equation for all the points. Again, the same exercise. Finally, you reach to a matrix which can be solved. Okay. So, when we were solving this governing equation, we were talking about conservative form and non-conservative form. What is the basic difference between the two? We will see here. Okay. Now, you tend to use that, tend to feel that conservative form is better. But that is not the experience of people. People have been using non-conservative form also. Okay. So, both the forms are useful. So, now we know that Navier-Stokes equations can be written in two forms. One is conservative form and the second is non-conservative form. Right? If you write your partial differential like this is the conservative form, you can write it like this and this will become non-conservative form. Okay. These two are same. There is no difference. Mathematically, they are exactly same. There is no approximation. Okay. So, the differential equation used in both the cases is exactly same. We have no problem with that. We are not violating the basic physics law or the basic equation. Okay. As far as differential form is concerned, the two forms of the equations are exactly same. Okay. However, when we discretize these two forms, we find that in conservative form, the principle of conservation is carried over to an individual cell, while in case of non-conservative form, the laws of conservation are not carried over to the individual cell. This is the law of conservation. In one case, you can find that it applies, in another case, it does not apply. And the reason for that is when you convert these equations into algebraic equation, finite difference equation, you are leaving out the terms which are called truncation error. Okay. And the truncation error is going to be different for both the cases. As a result, their algebraic equations become different. Right? I have summarized that in the end. Let us go to that so that you know what we are talking about. You look at this diagram. We have put both conservative form and non-conservative form together. As far as the differential equation is concerned, and I should write it PDE, partial differential equations, they are both same. Then this partial differential equation is converted into what? Algebraic equation and truncation error. Still they are same. We are following the mathematics. But what happens is their truncation error are different. When their truncation error are different, then their algebraic forms have to be different. Now, because the algebraic equations are different, then you find that in one case the conservation holds good, in another case conservation doesn't hold good. Right? At the cell level. So, this is what the non-conservative form and conservative form equation, what is the difference. Now, I'll go back and show you that how does it happen. Okay. So, we are talking about divergence in one dimension. We are just taking one example, small example. So, now this is our element. There are three, can say, cells or three elements which are next to each other, okay, and this psi represents the net mass of the fluid leaving per unit time the convection by convection or advection, properly known as advection. In CFD it is known as advection. So some mass is coming out from this, some is coming out this, some is coming out from this. So each of this cell is giving out some mass, right? Divergence tells you the net amount of mass which is coming out of a cell, of a volume, okay. Now you can all take all these cells together, right, and you can find what is the mass coming out. So this is psi A, psi B and psi C. So element A is giving out some mass which is psi A, element B is giving out psi B, and similarly element C is giving out psi C. Now if you put all these elements together, the mass which should be going out should be psi A plus psi B plus psi C. Now you will find that in one case it is so and in another case it is not so, and that is why this law of conservation is broken, okay, and that is why one form is called non-conservative form, the other is called conservative form. Now let us take this case. If you are taking this form, this is the amount of mass flowing out per unit time. Rho u is the mass flowing out per unit time, per unit area, and when you are multiplying by delta VL, it is telling you the amount of mass flowing out per unit time. Now you can calculate this psi, or this will be equal to rho u at I plus 1, rho u at I divided by the length multiplied by the volume, right? And then when you solve it, psi A will be equal to this, right? This delta x will be cancelled out with this, psi A will be equal to this, you cancel out this, and psi 3 C will be equal to this, okay. So you have these three equations telling you how much of mass is flowing out from each cell, each element, okay. Now you can say that the combined mass which is going out is this much. You add all this, you will find that this will cancel out with this and this will cancel out with this. So what is left is this much. Right? Because what is going out from one is entering the second, what is going out from the second is entering the third, and you add up, you get this. So psi A is equal to A plus B plus C. Now what you do is you okay, if you take all these elements together, so what is going out from the right is this, what is entering in from the left is this, total length is this, you divide by this, टोटल एरिया आ गया और आपके पास ये आ गया. तो या तो आप उसको ऐड कर लीजिए इंडिविजुअली, या तीनों सेल्स का वॉल्यूम सेम मान लीजिए. यू टेक इट एज वन कॉमन वॉल्यूम, देन यू डोंट टॉक अबाउट इंटरफेसेस, यू जस्ट टॉक अबाउट द लेफ्ट एंड द राइट. सो यू आर टॉकिंग अबाउट ओनली द लेफ्ट वन एंड द राइट वन. So either way you do it. You do it for each element and add it up, and you add all the elements and do it. You get the same answer. So which means that when you break a cell into smaller parts, conservation is maintained. Okay. Now let us take a different form, this. So thus we find that the net rate of mass fluid flowing out of the total volume by convection is equal to the sum of the net rate of mass flowing out separately of the different parts of the volume by convection. So if your conservative form of equation is written, then what will happen? If you have a bigger volume, you break into smaller parts. So either you find the conservation at the initial smaller part or at the larger part, it will be same. They will add up to 0 or they will be equal. You add up, flow from A, B and C, add up, that will be equal to the flow if you take the whole 3 cells together. Okay. Now you take another form, that we are taking this form. What we are doing, we are breaking the derivative in a different form. So 2 terms will be there. Now if you want to find psi A, this term will come out like this. Rho 0 you will have to take u1 minus u0, and for this it will be u0. Right? And then it will come out to be this. You do it for psi B, for B element B, it will be this. Right? And you do it for psi element C, it will be C. Now when you add it up, what will happen? You will get a term like this. Okay. If you take all of them together, it will be this. This is all the 3 elements taken together. Now this thing is not same as you add it up. If you add it up, you will have, I should have added that and put it here. Now रो u1 u0, इसमें से कोई कैंसिल होगा नहीं, ये तो u0 है तो इसमें से कैंसिल नहीं होगा, और u1 और रो1 रो2, तो all these will not cancel out. So you will have 4 terms here, 4 terms here, 4 terms here, 12 terms. And on this side you have how many? 4 terms. Right? They are not cancelling out. So let us now add the net rate of mass fluid over each cell, that is phi A, phi B and phi A. As calculated from equation this respectively and the net rate of this from this, now you will get this. So what do we find? We find that the second formulation, non-conservative formulation, the rate of mass of fluid generated in total volume is not equal to the sum of the rate of mass generated separately in different parts of the volume. Okay? Thus, the principle of conservation in the individual cell is not carried over to the aggregate of the cells. Right? So this anomaly arises neither because there is an error in the equation of the divergence, nor because there is an error in the process of discretization of the. These errors are not because of equations, original जो physical equation, and nor because the process of discretization. Nothing wrong. Instead, this happens because discretization process generates an error in the formulation. It expresses the differential equation as an approximation. It so happens that while in one instance the error is nullified by the error in the adjoining cell, in the other it does not. So what is happening? Your truncation error makes these two cases different. Now it so happens that the truncation error in one case cancels out completely. So the conservation is maintained, whether you take single cell or you say group of cells. While in the second case, that doesn't cancel out. So this is the basic difference. Okay. However, still we use the non-conservative formulation of this equation. But why? Now this is the question that needs to be looked into. At the smallest level, infinitesimally level, you find that equations are, you get the answer from both of them, right? So just like FDM method and FVM, in FDM we are not knowing that whether the conservation principle is followed or not, right? Same thing here, in a conservation form and non-conservative form, one, the conservation principle is followed, the other is not followed. So those errors are at the level of truncation error, and you can reduce them by reducing the size of the cell, right? So the solution you get is always approximate. CFD is always giving you approximate solution. So this is the thing which you should remember, that we are actually getting approximate solution. Okay. So we will close here.